Okay. Section 2.2. We're going to spread this out over 2 days. So yesterday we talked about just graphing parabolas the same way we graphed everything else in chapter 1, using just the transformations. And really, that's all you need. However, you can't tell what the transformations are unless you have it into what our book calls vertex form. Like, you got to have it looking like that. And this year I'm going to be teaching this in a way I usually don't teach it, because usually you don't start talking about parabolas in Algebra 2 until you've learned how to complete the square. And when you complete the square, you can get looking like this. Ooh. Sorry, didn't mean to yawn. I gotta get more sleep at night. You can, when you complete the square, what we're about to do with a little formula gets done more naturally, but we don't have much choice this year. We're not going to complete a square. You don't know how to complete a square yet. So we're going to do it the way we're going to do the book shows you how to do it, which is the opposite of the way I've ever done it before. So, it doesn't matter. We'll still be fine. But just talking about yesterday, remember the A, we know if that's positive, we're going to open up. If it's negative, we're going to open down. And just based on what the value of A is, like if A sits somewhere between 1 and -1, then it's going to be a vertical shrink. If it's, let's say this, the absolute value of it's more than 1, so if the A is greater than 1 or less than -1, then it's going to be a vertical stretch. Oh, also, A can't be 0, because if A is 0, then you don't have any x's. And then it's just a horizontal line, so that's kind of silly. It's just a constant function. The vertex, remember, is HK. The axis of symmetry, x is equal to h. And another way, this is usually how I think about the axis of symmetry. The part, let me see if I can get this pulled. Oh, there it is. There's a highlighter. There's one. If you take the part in this getting squared and you think about it being set equal to 0 in your head, like x minus h equals 0, then x equals h. That's usually the way I get the axis of symmetry. Okay, anyhow, there's another form about how to write a quadratic function, and it's in this form. And your book calls this the standard form, where instead of having it all looking like it looks when it's ready to talk about transformations, this is when it's all multiplied out. So whatever's the coefficient on the x squared, we call that A. Whatever the coefficient is on just the regular x term, we call that B. Whatever that constant is, we're going to call C. Gracious. So sometimes it's just, can you figure out what A, B, and C are? So if you look at this quadratic function in standard form, the A is -2, the B is 3, the C is 5. Okay, now if you've got terms missing, there is no x term, so that means there's 0x and there's a 1 here. So A is 1, B 0, C -9. This one's got the constant term missing. So A's -1/5, B's 3, C 0. So just being able to tell what the A, the B, and the C are, a lot of times it's just really handy. Here's why being able to tell what they are is really handy, because the way we're going to do it, there's 2 different ways of writing a parabola so far. There's the vertex form, and there's the standard form. But if you're using just all those are two different forms, it's just two algebraic manipulations of the exact same function that results in the exact same parabola. So no matter how you write it, it's going to be the same function. So what they're showing is, okay, what if we actually multiplied this out? Remember, that's just me going x minus h times another x minus h. So I get x squared minus xh minus xh plus h squared. So you get two of these. So that's where they're coming up with that. Then they're going to distribute the a. And they're going to kind of break it up. So this is the only one that has the x squared. This is the only one that has the x. These two don't have x's. So they're the constant on the end. So if this represents ax squared plus bx plus c, a is a. This takes the place of the b, and this takes the place of the c. Now, this thing down here taking the place of c, who cares if you know that or not? But this part of it right here is the key to how we're going to work our problems today. That negative 2AH with the x on it is the same as the b with the x on it. So if I divide both sides by x, so then x can't be 0, then these are the same. And if I just wanted to figure out what that h is, it'd be divide both sides by negative 2a. And that h value that sits right there in standard form, in vertex form, is the opposite of b over twice the a. But remember, axis of symmetry is x equals h. The vertex is hk. So this is going to be the x value of the vertex and whatever number the axis of symmetry runs through on the x-axis. That's the crucial part. This right here leading to this right here. So the axis of symmetry is x is the opposite of b over 2a. Okay. Now let's use it, because we're just kind of walking your way through it. When you write stuff in standard form, if a is positive, you know it opens up. If a is negative, you know it opens down. That axis of symmetry is going to be x is equal to opposite of b over 2a. And then right there, that point, the vertex, will be the opposite of b over 2a. Now, see how this right here replaces the k? It replaces the c. Like, you can use that. They're showing you how, but nobody ever does that. They just say the vertex right there is whatever the function is when you plug in the x that's going through the axis of symmetry. Okay, and then the y-intercept's important too. Like if you're looking at this, anytime you cross a y-axis right there, your x value is 0. So if you were to plug a 0 into this standard form, that disappears, f of 0 is c. So whatever that number right there is, that's always going to be your y-intercept. And that's what they're trying to show you on here, 0c. Okay, now let's actually use it so you can see what's going on. Standard form of the parabola. A is 3, B is -6, C is 1. So the axis of symmetry is that x is equal to the opposite of b over 2a. Opposite of b over twice A. So I've got an axis of symmetry at x is equal to 1. So right here at x is 1, there's the line that cuts it down the middle. If I want to know where the vertex sits, I'm going to take that 1, because you know the vertex lies on the axis of symmetry. I'm going to go back to my function, and I'm just going to plug in the 1 and see what happens. -3 plus 1, there's -2. So I know there's a vertex. I have x is 1, y is -2. Okay, definitely know we go through this point right here. A is positive. I know it opens up. So, and it's a little skinnier than usual. So once I've got, like, I don't want you to think you can't do this stuff we were talking about yesterday, because of course you can. Like, if I know it opens up, then I'm going to say this is at 1, -2. And I could go back and think about the parent function if I wanted to, which went through 1, 1. So over 1 up 1, but I'm doing 3 times as fast. It's going to sit here and go through right there. Over 1 up 3, up 3. But I can also look at it this way too. If I were to plug a 0 in for x, 3x squared is going to be gone. -6x is going to be gone. Leave me with 1. I've got a y-intercept at 1, which is usually going to be quicker than going, ooh, what's this vertical stretch doing? So then I could just match the points up. And if I wanted to keep getting points, because what I'm going to ask you is to always find 2 points on each side of the vertex. Like, I'd probably just go say, like, all right, well, where am I if I plug in the 3? Like, what happens at that x value? So 3, oops. Why is it not running? Come on. 3, dang, what's it doing? There it goes. 3 times 3 squared minus 6 times 3 plus 1. 3 times 9, there's 27, minus 18 plus 1 more. So 27 minus 18 is 9 plus 1, there's 10. So when I plug in a 3, I'm going to get out a 10. And then think of flipping that over the axis of symmetry. It's kind of ugly. The skinnier it gets, the harder it is to draw them. Especially when you can't draw like me. That's unacceptable. That looks too bad. There, that looks a little better. Now, this goes against every parabola graphing I've ever done, but that's okay. I'll live with it. This is the key to today. Okay. If this is labeled the axis of symmetry, we probably should. Let's try another one. So I know A is a half, B is -4, C is -2. Like, I already know, just look at this. I know it's going to open up, because whatever's in front of the x squared, that's the A. Because if it were to be factored out and gotten out of the way, that's it. So I know it's going to open up. I know it's going to be a little bit fatter than usual. And I know if I plug in a 0, I'm going to get out a -2. Like, I'm going to put that y-intercept on there first thing. Like, that is a point I can guarantee myself. And I can find that super easily. And then x is the opposite of b, opposite of -4, over twice that a. Half of 2 is 1. So at x is 4. 1, 2, 3, 4. There's my axis of symmetry. On the axis of symmetry lies the vertex. So let's see what happens when I plug x is 4 in. So half of 16 minus 16 minus 2. There's 8. I got a negative 18 out here. I got a negative 10. So if I came down right there, I've got a vertex. Now I can go ahead and line up another point over here at 8, negative 2. And then if I want to get more exact points, I think I just plug a 6 in. Because I don't want to have a fraction. That doesn't sound great to me. So I do a half of 6 squared minus 4 times 6 minus 2. 36, half of that's 18 minus 24 minus 2. What's that? Negative 6 minus 2 more negative 8. So it's 6 is my x. I get negative 8 as my y. And then I've got my parabola. Again, later in the year, once we've reviewed how to factor and you've learned how to complete the square, I will show you what I think is a much cleaner and, I don't know, not common sense, but let's just say better. I think it's a much better way of graphing a parabola. But again, it requires knowing how to complete the square. So, and the last thing for today is that there's some more terminology that we use when we're talking about parabolas. So when we discuss these quadratic functions, a lot of times they'll talk about a maximum value or a minimum value of the parabola. So if a parabola turns up right there, will be the lowest spot it ever gets to, the vertex. And we're going to have a minimum value of the function there. If it turns downward, ooh, I don't know what happened right there. Then right here, we can discuss a maximum value because the parabola is going to top out. And then also, going along with that, when you read a function going from left to right, we talk about whether it's increasing or decreasing or constant. Like going from left to right, my values for the y are falling as I go through here. That means that's a decrease in part of the function here, and then it starts increasing again over there. If you have a parabola that turns downward, it increases before it decreases. Okay? So this is just tell whether the following quadratic equations have a maximum or a minimum value, and then draw a quick sketch if you need to. The only thing they're talking about, a quick sketch, is, oh, there's a positive in front of the x squared. It opens up. So this parabola would have a minimum value. And for minimum and maximum, you're going to hear me just say min and max, because that's the calculus teacher in me coming out. We say minimum and maximum so much that people just say min and max. And it's okay if you, oh no, I have a typo. Dadgummit, I didn't fix it before I ran the copies yesterday. So that's not a parabola if that's not an x squared. Dang. All right, so right there, it's going to open downward because a is negative. So this one will have a maximum value. Now, this right here, negative 1/5 x squared, there's a maximum value, so it's got a max. Ooh, this one's not in standard form yet. I have to divide everything by 4. But that's still positive, so it's still going to open up. There will be a minimum value down there. Dang, can't believe that typo. Well, I can. I have typos all the time. Okay, not to go fix that in just a second. Now, here's particularly how you answer these. It says find the minimum value or the maximum value of the function. The minimum and the maximum values of functions will never be points themselves. Okay, so like right here in this function, there's a minimum value because it's bottoming out. But the value of the function, like let's talk about that. Hang on. Let's say I have a function that's 3x plus 2, and I plug in 2 and get an 8 out. The value of the function is 8. It's what generates out as your output when or at x equaling 2. Never, ever, ever give a minimum or a maximum value of a function as being an ordered pair. Okay, if you do that when you get to calculus, you're going to miss every single one of them. So we need to teach you right from the get-go. A lot of people will say that. They are wrong. You can't let the minimum or maximum value of a function be the ordered pair. Like the minimum value of this function is 1, and it happens when x is 1. Okay, now this parabola tops out. So let's write the whole sentence. The function has a maximum value of 7 when or at x equals -1. So again, if they said when's the minimum or maximum, or what's the minimum or maximum value, it's always going to be the y value. And you just tell them at what x that happens. Okay. And then the other thing they want us to do, describe the domain and range. All right. So for this A one, you can plug in any x you want. So x is an element of the reals. The range, though, well, hang on. I'm trying to get fancy. Let's say it's all real numbers. And then the range, see how the lowest, because it's the minimum value, ever was 1? So my range is all these y values right here are 1 or bigger. So this one, domain, all real numbers, because I can plug anything I want, x, y's, into that parabola. But the range, it tops out at 7. All the other y's are smaller than that. I like how that R looked. Okay. All right, another thing, tell where it's increasing and decreasing. You read it left or right like you read a sentence. So this function increases and decreases. It decreases to start with because we're heading down. It decreases to the left of x equaling 1. So a lot of times people just say it decreases when x is less than 1. It increases to the right of x equals 1, or when x is greater than 1. Now, depending on what definition of increasing and decreasing you use, we're not going to get super specific. Like we didn't even give a technical definition. In calculus, a lot of times right there at x is 1, they'll include that as being, it's like the last of the spot it decreases and the first of the spot it increases. So a lot of times you'll see them in calculus, they'll include that in both, which seems counterintuitive. That could be both, but it's just based on whatever definition you use. We're not going to lose any sleep. We're just going to say to the right and to the left and be done with it. Okay. But right here, we're increasing and we're decreasing right there. And if you just want to label it on the picture, I'm okay with that. That's fine. All right, I think that gets today. I think I've discovered I'm getting up this early and making these is not working out for me because I keep making silly mistakes. So here we go.